I want you to imagine a humid summer morning in the late 19th century when the idea of controlling indoor air felt more like magic than engineering. Long before anyone spoke of smart thermostats or low global warming potential refrigerants, people wrestled with heat the same way they had always done: shading windows, hanging wet sheets, and retreating to cellars. The desire to control temperature and humidity was often born of industry rather than comfort. Breweries, textile mills, and printing houses needed consistent conditions for quality and productivity, and it was this industrial need that sparked experimentation with cooling rather than the pursuit of personal comfort alone. And this is, and not only that, I will talk about today on Knowing is Winning, about the past and the future of air conditioning. The story of modern air conditioning has roots stretching back farther than most listeners expect. In the mid 19th century, an American physician named John Gorey built machines to make ice motivated by a desire to cool hospital wards for fever patients. Gorey's machines used compressors and were powered by steam or horse-driven mechanisms. He received a patent in 1851 for his ice-making device. His vision of mechanically cooled rooms was technically fragile and commercially impractical in this time. But it planted a seed. Cooling could be engineered, not just improvised. Fast forward to the turn of the 20th century, and you meet Willis Carrier, who is widely credited with inventing the first modern electrical air conditioner unit in 1902. Carrier wasn't trying to make people more comfortable. He was solving a moisture and humidity problem for a printing plant in Brooklyn where paper and ink were failing. Carrier's brilliant insight was to treat air the same way one treats water in a steam system. Remove moisture to control humidity and temperature simultaneously. His early units were bulky industrial affairs designed to condition entire rooms for process control rather than living rooms or cars. But his work set the technical foundations for refrigeration cycles, humidity control, and the engineering principles that make air conditioning possible today. As the technology matured through the early 20th century, air conditioning shifted from factory floors into public life. Movie theaters, department stores, and luxury hotels began to install cooling systems, and the social effects were enormous. People could gather comfortably in summer, commerce extended to hotter seasons, and architecture shifted to rely on mechanical cooling rather than passive design alone. In the United States, this diffusion of air conditioning reshaped cities, migration patterns, and even the economy. Southern cities grew and industry relocated in ways that would have been impossible without reliable mechanical cooling. These social and economic ripples are part of the technology's legacy as much as the machines themselves. Now, the basic thermodynamic engine behind the most conventional air conditioners is the vapor compression refrigeration cycle, a triumvirate of compressor, condenser, and evaporator through which a working fluid, the refrigerant, circulates. The refrigerant absorbs heat from indoor air as it evaporates at low pressure, then is compressed to a higher pressure and temperature, and rejects heat to the outdoors as it condenses. Over the decades, the refrigerants used in those cycles evolved from toxic or flammable early chemicals to chlorofluorocarbons, then to hydrochlorofluorocarbons and hydrofluorocarbons, and now towards natural refrigerants such as propane, ammonia, and CO2. Each transition was driven by a combination of performance, safety, environmental regulation, and, of course, cost. Science and engineering never pause, and the last 2 decades have seen a focused push to make cooling more efficient and less damaging to climate. The reason is simple. Heating and cooling account for a huge fraction of global energy use, and air conditioning is a fast-growing slice of that pie as incomes rise and hotter climates expand. Engineers and researchers have attacked the problem on several fronts simultaneously. Improving the efficiency of compressors and heat exchangers, developing inverter-driven motors that vary power smoothly instead of cycling on and off, recovering waste heat to preheat domestic hot water, and redesigning ductwork and controls to avoid losses. These incremental improvements, when combined across millions of units, add up to a significant energy savings and peak load reductions for electric grids. Parallel to improved components is the growing intelligence embedded in systems. Modern air conditioners are not dumb boxes anymore. They are networked devices integrated into smart home ecosystems and industrial building management systems. Edge computing, machine learning, and simple occupancy sensors let units learn occupant behavior, predict cooling demand, and smooth energy consumption to avoid sudden peaks. Predictive maintenance algorithms scan compression vibration signatures, refrigerant pressures, and power draw to flag deteriorating performance before failures occur, increasing reliability and extending service life, of course. The result is not just convenience, but measurable reductions in lifetime energy use and operating cost. Material science has been quietly changing the game too. Heat exchangers now use the microchannel designs that increase surface area and improve heat transfer with less refrigerant charge. Coatings and surface treatments reduce fouling and corrosion, especially in coastal and polluted urban environments. Magnetic refrigeration, a less familiar but promising approach, uses magnetocaloric materials that heat and cool when exposed to changing magnetic fields, potentially offering higher efficiency without traditional refrigerants. Solid-state cooling approaches, including thermoelectric and electrocaloric systems, remain limited by materials performance and cost, but rapid advances in materials research keep them on a roadmap as a possible disruptive technologies if key hurdles are, of course, solved. On a system scale, district cooling and absorptive cooling offer alternatives to the single-room split units. District cooling centralizes chilled water production for entire neighborhoods or campuses, delivering cooling through insulated distribution networks. This centralization improves the efficiency through economies of scale and allows integration with waste heat recovery or low temperature sources such as seawater or deep boreholes. Furthermore, the renewables and cooling are intersecting in interesting ways. Solar cooling marries photovoltaics or solar thermal collectors to either electrically driven systems or absorption chillers. In southern climates, where cooling demand is correlated with solar abundance, pairing PV arrays with efficient inverter compressors and thermal energy storage can shave peak demand and reduce grid stress. Thermal batteries, tanks of chilled water or phase change materials, store cooling capacity produced during off-peak and sunny hours, then dispatch that stored cold during evenings. These hybrid systems allow buildings to shift their load profile, participate in demand response programs, and reduce reliance on fossil fuel peakers. The user experience of cooling has evolved as well. Zoned HVAC systems let different parts of home or building run at different temperatures tailored to occupancy, reducing overall energy use and improving comfort. Variable refrigerant flow systems and multi-split engagements allow capacity to match demand with fine granularity. Noise reduction, indoor air quality sensors, And integration with ventilation systems mean that modern air conditioners do more than lower temperature. They manage humidity, filter particulates, and in some designs recover energy from exhausted air. In the wake of global health concerns, interest in ventilation, filtration, and controlled air exchanges has risen, pushing new designs that balance fresh air supply with energy efficiency. Modern air conditioning systems have evolved far beyond simply cooling the air. They now play a vital role in improving indoor air quality by actively reducing bacteria, viruses, and other airborne contaminants. At the heart of these systems are high-efficiency filters such as the MERV 13 or even HEPA filters, which are capable of capturing microscopic particles, including many bacteria and some viruses. These filters act as the first line of defense, physically trapping harmful particles as air circulates through the system. But filtration is just the beginning. Many modern systems incorporate ultraviolet, germicidal irradiation, UVGI, using UVC light to neutralize pathogens. Installed within air handlers or ducts, these UV lamps emit a specific wavelength that disrupts the DNA or RNA of microorganisms, rendering them inactive and unable to reproduce. This method is particularly effective against airborne viruses and bacteria, including those responsible for respiratory illnesses. Another layer of protection comes from ionization technologies. Bipolar ionization systems release charged ions into the airflow, which attach to particles like viruses and bacteria, causing them to clump together and fall out of the air or become easier to capture in filters. Some systems also use photocatalytic oxidation, which generates reactive molecules that break down organic pollutants and microbial threats at a molecular level. Humidity control is another subtle yet powerful tool in the fight against airborne pathogens. By maintaining indoor humidity levels between 40 and 60%, air conditioning systems can reduce the number of viruses and bacteria, which often thrive in overly dry or excessively humid conditions. Yet remember, the cleanliness of the system itself matters. Modern HVAC designs often include antimicrobial coatings on coils and drip pans, and some are equipped with automated cleaning cycles and support periodic fogging with biocidal agents. These measures help prevent the buildup of mold, biofilms, and bacteria within the system, ensuring that the air being circulated remains as clear as possible. Together, these technologies form a multi-layered defense that transforms air conditioning from a comfort feature into a cornerstone of public health. Whether in a hospital, office, or home, these systems are quietly working behind the scenes to make the air we breathe safer and healthier. Actually, there are more intriguing emerging technologies worth watching closely. Liquid decussant systems use hygroscopic solutions to decouple humidity control from sensible cooling, improving comfort and efficiency, especially in humid climates. Membrane-based dehumidifiers and novel heat pump architectures that integrate evaporative cooling with compression cycles can reduce energy use. Advances in compressor design like multi-stage and variable speed scroll compressors increase system COPs at part load conditions where most systems spend their life. Additive manufacturing and modular construction techniques are enabling more compact, serviceable, and recyclable components, easing maintenance and reducing embodied carbon over product lifetimes. Another frontier is the integration of cooling with the broader energy system. Smart grid-enabled HVAC units can act as flexible loads, participating in demand response and ancillary services. Aggregated fleets of air conditioners can provide frequency regulation by momentarily modulating power while preserving indoor comfort. These capabilities require secure communications, robust control algorithms, and fair compensation mechanism for consumers, but they represent a powerful lever for balancing increasingly volatile supply from renewables while leveraging existing assets, installed HVAC units, rather than building new infrastructure. If you walk into a modern building today, you will see these threads in action, sensors stacked discretely in ceilings, ducts carefully balanced by building commissioning teams, condensers placed to avoid heat recirculation, and building management systems running optimization routines overnight. Manufacturers compete on efficiency ratings, refrigerant safety, and life cycle impact, while governments steadily tighten performance standards. The evolving market rewards not just cheap kilowatt-hour consumption, but smarter systems thinking that considers whole life emissions, serviceability, and adaptability to future refrigerants and grid conditions. As we look ahead, I want you to picture a near future where most homes have highly efficient heat pumps that cool in summer and heat in winter, where solar panels paired with thermal storage shave peaks, where district cooling plants use low-carbon electricity or waste heat, and where urban design softens heat in islands so neighborhoods need less mechanical intervention. In the future, advanced materials and solid-state cooling may have found niche applications that avoid greenhouse gases altogether for specific uses. And control systems coordinate millions of units to stabilize grids and reduce overall emissions. It is an ambitious vision, but the tools and momentum are already in motion. What's needed now is scale, smart regulation, and equitable financing to bring those benefits in every community, not just the wealthiest ones. The invention of air conditioning is a quintessentially modern story, one that ties together physics, industry, public health, architecture, and social change. Its future will be written by interdisciplinary collaboration. Material scientists improving coloring materials, electrical engineers refining variable speed drives, urban planners redesigning green spaces to reduce heat, policymakers drafting refrigerant phase downs, and entrepreneurs creating business models that finance retrofits in low-income neighborhoods. If you take one idea away, let it be this. Air conditioning is not a single invention with neat finish line. It is an evolving system of technologies and choices. From Gory's ice machines to Carrier's industrial dehumidifier to today's AI-driven heat pumps and district systems, the arc bends towards greater control, efficiency, and accountability. So when you feel that first cool breeze from a well-timed compressor kick in, remember the log chain of curiosity, calculation, and compromise behind it. Early inventors solving industrial puzzles, companies scaling up technologies, regulators nudging the market away from harmful chemicals, and researchers pushing toward greener, smarter systems. The humble act of making air cooler is a mirror reflecting our capacity to solve complex problems when science, policy, and human need converge. And this was Knowing is Winning. Thank you very much for watching.